Okay, so identity based encryption. So this was introduced by Samir in 1984. So the idea is to use the ID as a public key. So because in the public key setup, what we have many users, say Alice, Alice, Bob, sorry, so Alice, Bob, Rob, Palas, okay, and in the public key crypto system, so we need to have everybody needs to have a public key private key pair. EB, sorry, ER, DR, PP, DP, and then everybody's public key should be stored somewhere, which is a public key directory, PKD, which is storing the public key of Alice, Bob, Rob. So so it's a long message, long string. So EB, ER, EP, so on. So usually in public key setup, so this public key directory has to maintain, and problem there are many issues like who will, so anybody can, so this should be publicly available. So there is question of trusted party, so whom we can trust to maintain this public key directory, and then again asking the public key. So these are the issue, or certificate, or we can have a public key certificate. So if somebody wants to send, suppose Bimal wants to send a message to Palas, so Bimal has to get the public key for the Palas. So or Palas has to show Bimal that this is my certificate, public key certificate. So this is a very to get rid of this this headache. So Samir introduced this identity based encryption. So we use the identity as a public key, and so basically we use the identity as a public key, and to get the corresponding secret key, so we need to so key generation center, there is a key generation center. So this is a users, so UI, so users is having a identity. So identity also need to convert into 0-1 string. So what user will send? User will send this ID to this key generation center, and the key generation center will give the, so key generation center choose some, this is the setup phase, choose some public parameter. We'll discuss what are this by an example. This is parameter and is having a master key, which will be used to get the secret key corresponding to the users. I mean, which will be used to get the secret key corresponding to that ID. Okay. So so it's sending the ID, which is basically 0-1 string of any length, and it should give us giving us the secret key of UI, and then this pair SKI, and so after getting this, So SKI, ID is the EI and this SKI is the DI. So this is the public key and secret key pair of this. And but when the encryption will be done, in the encryption we need to use the public parameter. This parameter set is public, but this is the master secret key of the key generation center. This is the master secret key, which will be used for generating the secret key corresponding to the ID. So basically it has this step. First step is setup phase. So steps for identity based encryption. So first one is setup phase. We should run the setup phase or key generation phase. In the setup phase, we choose the parameter, the public parameter. We say it param and the master key, which is secret to this key generation center, and then the key generation, which is named as extract. We extract use the master key and the ID. So say use the master key and the ID. This is the ID of user 1, and use the master key. We should be able to generate the secret key of the corresponding users. And then the third step is encryption. Encryption or encrypt. At the encryption, so now we have this is basically now Alice wants to send a message to Bob. So Bob has received Bob is having his ID. So this ID could be ID of Bob. So ID could be say email ID, a unique identification number, email ID or a fingerprint. This biometric, the fingerprint could be ID of the Bob. We can use the fingerprint as a ID. Okay. So any unique identification of that person is called ID, but it has to convert into binary. So then Bob will, so this is the key generation center, which at the setup phase choose to param, this is public, and a master key which is secret. So Bob send his ID of Bob and get back the Bob DB. So this is Bob EB. So Bob EB, Bob DB. Okay. And this is now this is done. So now Bob is having the public key. Bob is having the. Now Alice can send a message to Bob using this Bob public key, which is getting from the this and that can be Alice can get this from the KGC key generation center also, and then Alice can encrypt and send a message to Bob. And the fourth step is the decryption. We will come to an example. The decryption. Okay. So this is to overcome that headache of certificate or the public key directory. So basically we can use the identity as a public key. Identity could be email ID, biometric, anything. Okay, let us talk about a ID based example of ID based encryption, which is by Bilinear and Franklin. And this work was published in Crypto 2001. Bilinear and Franklin, identity based encryption. This is Crypto 2001. This work has published. Okay, the full paper can be from there. Okay, so it is basically used the bilinear map. So let us recall the bilinear map or bilinear pairing. So suppose we have two cyclic group G and GT, two cyclic group, multiplicative group. Cyclic group of order P. So we have two groups of order P, G1 and G2, and then we defined a map E, which is for G and GT, and now we defined a map from G cross G to GT. Okay, so it is taking two element from, so E of UV belongs to GT, where UV both belongs to G. So it is basically a mapping from G cross G to GT. So we take two element from G, and then that mapping, then that will map to the element in GT. So this will be called a bilinear map if it satisfies some properties. So what are those properties? So okay, the first property is E of U to the power A, V to the power B should be equal to E of UV to the power AB, and this is true for all UV belongs to G and all AB belongs to ZP. Okay, let us understand this. So U of A means U times, U of A means U times. So this is a multiplicative group, G is a multiplicative group, G is a multiplicative group, and of order P. So that means if we take, so this is basically G, A times A times. So this is also will be belongs to G. Similarly, V is belongs to G. So that means if we operate V, B times, V into V into V, B times. So this is basically V to the power B. This will be also belongs to G. So if this two belongs to G, then we can talk about their E. I mean the map, because map is defined from G cross G to GT. Sorry. So we can talk about their this mapping. Now this should be equal to E of UV to the power AB. So this AB means this dot is basically modulo operation modulo P over the ZP, that is our underlying field. So this is the first property. So it must satisfy this bilinearity property, and so this is the first property, and if G is a generator, then EGG should be generator of GT. So second is if G is a generator of G, then EGG is a generator of GT. Sorry, GT. So that means EGG should not be equal to 1 in GT. I mean the identity element in GT. If it is identity element, it cannot generate the group. So this should not be equal to identity element of GT. So this is the so if G is a generator of this, then EGG is the generator. So this we have seen. Now the third property is we should have some algorithm to compute this EUV for all UV is efficiently computable. Efficiently computable for all UV belongs to G cross G. Otherwise, nobody will. We should able to compute this actually. Okay, so if these properties are satisfying, then we call this is a bilinear map, and this we have used for Jokes protocol, if you remember, for key exchange, for three party key exchange in a single round. Okay, so now the example of such a map is, so this you can take a note, but this is not in our syllabus. This example, Tate pairing and well pairing, Tate pairing and well pairing from the elliptic curve. These two are example of bilinear map. So, but it involves some algebra, divisibility theorem to develop this state pairing well pairing. But for this course, we are not going to the details of this construction, but we will use this for our construction of IBE. Okay, so we will use this bilinear map in IBE, Bonnet-Fengling. So this is the Bonnet and Fengling. Okay, so setup phase. So at the setup phase, we choose a P and G, GT, and G is a generator and a bilinear map. So this P is prime and G and GT are two multiplicative group, cyclic group of order P, and G is a generator of G and E is the bilinear map. So this is the we choose, and then we define the parameter, public parameter, as this P, G, Q. We define Q and two hash function H1 and H2. So what are H1, H2? Where Q is basically G to the power alpha. Alpha should be the master key, and H1 is the hash function which takes the any. So this is basically, this will convert the ID to a element in G. So this to G. So it will, because ID could be anything, a biometric, fingerprint. Okay, then fingerprint has many characteristics in this. So it actually, I think 40 or some possibilities are there. So, then we can convert into matrix, then we can convert in, this is basically an image, we can convert into matrix, and then that matrix we can convert into a vector like this. So, anyway, so this is basically any arbitrary length 0 1 vector, and then it will convert to a group element G. So, this is the hash function we use, and another hash function H2 is basically it takes an element in GT and it will convert into L bit length. So, this is the public parameter, and the master key is basically this alpha. This alpha is the master key. Okay. Now, this is the setup phase. So, now let us talk about how to get the secret key for the users. Okay. So, public key, this is the key generation center, and we have users over here, UI. Okay. So, it is having the param and the master key. Now, it sends the ID. So, ID is basically this must be a 0 1 string. It is a biometric, we convert into a 0 1 string. It is a email ID. So, we convert into ASCII value, then we convert into binary string. So, everything can be converted into binary string by a proper correspondence. Okay. Now, what will be the secret key? So, secret key of this users is basically H1 IDI to the power alpha. So, this is the secret key of the user. So, basically, so H1. So, we take the ID. So, H1 if you remember, H1 is a form, it is take any arbitrary size length, convert to the some element in G. So, this will be the G element in G. Now, we can take to the power alpha. So, this is basically the secret key of this ID. Okay. So, now, so this is the key generation. So, we got the ID of the users. Now, how about encryption? So, through encrypt we need the public parameter. Encryption. Okay. So, just recall, we need to have this public parameter is basically P comma G comma Q, which is basically G to the power alpha H1 H2, and we have the ID, which is the public key of the users, and secret key of the users is we got from the this key generation center. Okay. So, and the message is basically a length of L bit. Okay. So, it is generate a ciphertext CT, which is have two parts C1 and C2. It is similar to the L-gamma encryption C1 and C2, where C1 is basically G to the power R. R is chosen randomly from ZP. So, this means randomly for ZP. Okay. And so, this is C1 and C2. Other part of the ciphertext is basically masking M XOR with H2 of E of H1 of ID. If we take the H1 of ID, it will be an element in G, and then we have Q. Q is basically G to the power R. So, this to the power R, and then after this we take the we take the H2 on this. So, H2 on this. So, this will be an element in GT, because this is basically H1 of, this is an element in G and this is an element in G. So, this will be an element in GT. So, this will be an element in GT, and then H2 will convert into again H2 is a mapping form. If you recall, H2 is basically a hash function GT to 01 to the power L, because our matches is L bit. So, we can do the XOR with this. So, this is the encryption which Alice is doing for Bob. So, Alice is sending this message to Bob. Now, how Bob will decrypt it? So, this is encryption. So, decryption is basically so how Bob will decrypt it? So, Bob will just do this thing. M is basically so Bob is receiving C1 C2. So, Bob will just do M is basically C2 XOR with H2 of E of SKID comma C1. E of S. So, this is the Bob secret key. So, Bob secret key and C1 it is getting from the ciphertext. So, it will compute this E of SKID and C1 and apply H2. So, H2 will be again a L bit, and this should give us M. So, what is the correctness? So, if we just check this quantity, so this should be M. So, if we just check this quantity, this is basically C2 C2 is basically what? C2 is basically M XOR with this, M XOR with H2 of E of H1 of ID Q to the power R. This XOR with, we are doing H2 of E of H1 of, this is basically ID to the power alpha and G to the power R. So, this is basically M XOR with, so this term will be same. So, H2 of E of H1 ID G to the power alpha R and H2 of same thing E H1 ID comma G to the power alpha R. So, these two will give us M. So, this is the correctness of this. So, we get the message. So, this is the identity based encryption, where we will use the ID as a public key to avoid this certificate or to maintain this public key directory. So, ID could be anything, fingerprint or any email ID or any unique identification of the users. Thank you.